Okay, guys, welcome. So today we're going to talk about modeling of free oscillations of a mass spring system. So what we mean by free oscillations is that we are not forcing any motion here. We're just sort of seeing what happens if we have a mass spring system and we want to see sort of what happens to it, right? So sort of the model that we're going to consider here is that we have some spring, which is in this picture here, and we're going to attach some mass to it, some sort of weight to it, right? Now, we want to see sort of what happens once we have displaced this spring, right? So that's sort of what we're going to look to model here. Okay, so again, sort of the setup here is you're taking a spring, and of course the spring, as it does, will resist extension and also compression. It wants to sort of be at a fixed sort of level there without it being compressed or extended. And we're suspending it from some sort of ceiling or something, and we're letting y equals 0 denote sort of the position when the system is at rest, right? And then we want to sort of model the activity at that point. Now, one thing that we're going to do is we're going to choose the downward direction as positive. So that way, when the spring is extending, we have that sort of positive motion. And when the spring is compressing, that is sort of your negative motion, right? Now, we can show that the spring force by Hooke's law is sort of this F1 times negative ky. And essentially what that means is that this is sort of the reason why it's negative, because the system wants to come back to rest. So it wants to eventually come back to 0. Wants to return to rest. Right, and depending on sort of the stiffness of the spring, if the spring is rather stiff, then that means that your K value is going to be large because it's going to come back to this level very quickly. And if it's not a stiff spring, then your K will be small, which indicates that it's going to sort of be much looser in terms of it returning to rest. Right. One thing that I guess we should note here is that this K term is known as the spring constant. It's actually right here, so we'll steal that. So K is the spring constant. So that's one terminology that we'll see sort of coming here. Okay. Now we also have, of course, that gravity is going to be acting on this. And of course, most of the time, depending on what system we're working with, if you're using the metric system, we take our gravity term to be 9.8 meters per second squared. And if we are using the American system of using like feet and yards and stuff like that, then it's 32.17 feet per second squared. Of course, this doesn't really show up in, well, no, I shouldn't say that. It doesn't show up, I guess, explicitly, except sort of in the terms of what our M is, right? Not our M, but it's going to come up in our force, I guess. Okay, so, right, so now, of course, this is determined by Newton's second law, which says that if you take mass times acceleration, that's going to give you the force. Okay, so let's first talk about what we mean by an undamped system. Okay, so what we mean by damping is that it's something that's sort of slowing the system down. Now, every physical system, at least in our world, has some sort of damping, because if it didn't, it would just move forever, right? Even like if you watch a pendulum swing or whatever, there's very little damping on it, but it's not going to run forever. So there is some sort of damping on it. But a lot of times what we do is that if the damping is small and we only consider what's going on in the system for a short time, what happens is that we sort of chalk up the damping as negligible and we sort of disregard it. So what happens is that we give this system an ODE of m times y double prime plus k times y is equal to 0, which of course is a homogeneous linear ODE with constant coefficients. So of course what we could do is we could obtain a general solution as we sort of discussed in the previous video. And after some work, you'd eventually arrive after setting omega 0 equal to the square root of k over m, which is basically just coming from dividing through by m. And then once you set up your ODE, you're going to see that you're going to get imaginary solutions, and your imaginary part is going to be that square root of k over m, right? So that's not too hard to find, but we're just going to present it here sort of without proof. If you want to verify it on your own, go for it. But that is our general solution in the undamped system. Now, of course, what happens here is that you get some oscillation, right? Which is what you should expect. Sort of, again, thinking back to the pendulum example, that's sort of, equivalent in this case, I guess. So you're seeing that depending on what your initial velocity is, you have some sort of different mechanical phenomena here, right? So if your initial velocity is positive, right, then your position, of course, is going to extend from its initial position and then start to compress, and then it's going to extend again, and so on and so forth. If it is 0, then of course the spring is going to try and pull back the weight, and then it's going to continue its oscillations that way. And if the initial velocity is negative, you get sort of more of a strong version of the 0 initial velocity case. Okay, so that's sort of a nice visual graph as to what's happening there. Now, depending on the particular problem that you're looking at, sometimes it's an advantage to think of your general solution in this way, because then you can talk about your physical characteristics of tangible objects like amplitude and phase shift. So we can define our y of t to be some c, which is actually square root of a squared plus b squared, times cosine of omega 0 t minus delta, where delta is the tangent of b over a. Or I should say inverse tangent of b over a. Okay, so let's look at an example. So if we're looking at a mass spring system with an iron ball of weight 98 newtons, and it can be regarded as undamped, and the spring is such that a ball stretches at 1.09 meters, we want to know how many cycles per minute will the system execute. What will its motion be if we pull the ball down from rest by 16 centimeters and we let it start with, say, a 0 initial velocity? So basically that last sentence is going to give us some initial conditions to get the particular solution. Right, so what we do is we know that by Hooke's law, right, we know that F is equal to negative K times Y, and the negative force is given by the weight, and the 1.09 stretch is going to give us this equation where we have W is equal to 1.09 times K. Right, and of course you can solve for K. In this case, we know that W is 98, so we could plug that in for W, and we get that our K value is 90, right? So sort of what that's going to allow us to do is that's going to allow us to calculate the mass, right? So of course, your weight is equal to the mass times gravity, and here we're going to take G, we're going to take our gravity to be 9.8. Since we're working in the metric system here, remember we were told that we stretch by 1.09 meters. So we're going to take gravity to be 9.8, and using the fact that our original weight was 98, we can find that W is equal to 10 kilograms. Okay, so now we can say that our frequency is this omega 0 omega 0 over 2 pi, and again, omega 0 is the square root of k over m, which we can find to be 3, and of course, that will give you this frequency of 0.48 hertz. All right, now the important thing is that your general solution, remember, is yt of a cosine omega 0t plus b times sine omega 0 times t, where omega 0 is square root of k over m. And in this case, square root of k over m was 90 over 10, which is square root of 9, which is 3. So that's where these 3's are coming in for your general solution. Okay, now we can use our initial conditions. So we know that y of 0 is equal to 0.16 meters because we pulled it down by 16 centimeters at the start, right? So if you convert that to meters, you're looking at y of 0 is equal to 0.16. So now if we use that in our general solution, of course, you're going to get that a is equal to 0.16, because if we plug in a 0 for x's, we're going to get 0.16 is equal to a times cosine of 0, which is 1, plus b times sine of 0, which is 0. So you get pretty quickly that a is equal to 0.16. Now, if we assume that we have a 0 starting velocity, what's going to happen? Well, we're going to get that 0, first of all, y prime, is negative 3a sine of 3t, and then we get a plus 3b cosine of 3t. So if we plug in our initial condition for this, we get 0 is equal to negative 3a times 0, and we get plus 3b times 1. So this goes away, and you get that 3b is equal to 0, which of course you conclude that b is equal to 0. So then plugging that in, we can get that the particular solution is given by 0.16 times cosine of 3t. Okay, so that's our particular solution. And now we can talk about what we mean by a damping force. Okay, so now when we add a damping force, basically what's happening is that we are basically, so I think let's look at this example here. So we're connecting these, physically we are connecting the ball to a dash pot, which is basically, which is given by this figure here, right? And of course that's going to essentially slow down your system here, right? So it's going to make the system basically come to rest quicker, right? So now you have this extra term in your ODE, right? So now you have that m y double prime plus c times y prime, so you're now getting that middle term plus k times y is equal to 0. Okay. So of course, c is the damping constant. We'll refer to it as the damping constant. And c has to be positive, of course, because c is acting against the motion, right? So it's sort of stopping the motion. Now, of course, to find a general solution, we would divide through by m, and our ODE is going to be given by this equation 5 right here. And if you use the quadratic formula, you're going to get that these are your eigenvalues. All right, so again, we get 3 cases just as we did before. Basically, you either get 2 distinct real roots, you get a real double root, or you get complex conjugate roots, right? And again, that's dependent on what's happening underneath the square root here. Okay, now just to allow me to be lazy, we're going to call the real part of this alpha. I guess it's going to be negative alpha, and we're going to call the second part of this, which may or may not be imaginary, we're going to call that beta. All right, so that basically we're just going to allow this to say that my two eigenvalues are negative lambda plus or minus beta. Okay, so the first case that we're going to discuss is what if you have what's called overdamping, which essentially means that so this is when you get the two real cases, so you get the two distinct real roots. So we know that the general solution is just given by e to each of those two roots, multiplying by arbitrary constants and add them together. What does this mean physically? It means that when you have overdamping, it's going to zap the energy out of the model quickly, and you're going to arrive at something where you have no oscillation fairly quickly. One thing that you can note here is that both terms in the solution go to 0 as t goes to 0. So what's going to happen is you're going to get a model, regardless of its initial displacement or its initial velocity, is going to converge to 0 rather quickly, right? And that's because the damping is strong enough that it's taking the energy out of the system very quickly. So that's sort of what we mean by overdamping. Now, the interesting case that we're going to look at next is what's called critical damping. So now this is the case where you have this beta part equal to 0, so you get the repeated double real root, right? Which in this case will just be negative alpha. Now, of course, the general solution, which we talked about in the previous video, will be you're going to have this e to the negative alpha times t in both terms. And then, of course, one of them is multiplied by arbitrary constant, C1. The other one is multiplied by arbitrary constant, C2, times t. Okay. One thing to note here as well is that this can only pass through y equals 0 at most once, right? And the reason why that happens is because e to the negative alpha t can't be 0. And this C1 plus C2t is linear. And of course, that can only pass through the origin one time, right? So what's happening here is that, again, you're going to sort of approach 0, but not as quickly, right? And when you have these sort of situations here, you sort of see that you can only pass through the origin sort of at one time, right? Not the origin, but when y is equal to 0, you can only approach that once. Okay. So, and we can actually say one more additional comment about critical damping once we talk about underdamping. Okay. So in the underdamping case, this is when your beta term is imaginary, right? And we're going to call beta equal to I omega star just because it's a little different than the omega in the last video. So I'm going to refer to it as omega star. So now your two eigenvalues are given by negative alpha plus I times omega star. So of course, we have now two different ways that we can present this solution based about what we talked about a little bit earlier. This is coming directly from the general solution for an ODE of this form. You're going to get e to the negative real part times, I guess the real part is just negative alpha times t, and then you get this sum of cosine and sine terms of the imaginary components. All right, and of course, in this physical setting, it is also helpful to have it in this form as well. But let's go ahead and we'll take a look at what that means. So what now happens is that you're going to get sort of this oscillating system that's going to happen forever, but the oscillations get smaller and smaller sort of as t goes on, right? So what's happening is that this exponential term, this e to the minus alpha t, is going to 0 as t goes to infinity. So that's sort of making the amplitude smaller as t gets bigger, but the cosine and sine terms are giving you that oscillation, right? So one thing that is sort of that we can now say about critical damping is that critical damping is what happens sort of right before you start to get oscillations, right? So it's sort of that in-between case. Okay. So to wrap this all up, let's look at a couple of different examples. We're now going to look at the first example, but now with a damping term, right? So we're now looking at this ODE, and we're going to consider where we have 3 different levels of damping. We're going to consider when C is 100, when C is 60, and when C is 10. So of course, in the first case, right, of course, remember from the first example that we found that M was equal to 10 and that K was equal to 90. And here we're assuming that C in this first part is 100. So once we evaluate that into our ODE, we're going to get this, which gives us this characteristic equation, which is going to give you these 2 characteristic values or 2 eigenvalues. So that gives us that the general solution is the sum of e to the negative 9t times an arbitrary constant C1 plus C2 times e to the negative t. And to find our initial, our C1 and our C2, again, we use the fact that these were our initial conditions. And for time's sake, what will happen is you're going to get C1 is equal to negative 0.02 and C2 is negative 0.18. So this gives you the overdamped solution. Now, one thing that's going to happen here is that this is going to go to 0 very quickly. Right, because these are very quick exponential growth or decay, sorry. And your amplitudes are small as well, so that's another thing to note. Okay, in case 2, we're now considering that C is equal to 60, and again, M and K are what they were before. So again, we'll get the characteristic equation 10 times lambda plus 3 squared, so we get the double root scenario, which allows us to say that our general solution is e to the negative 3t times an arbitrary constant, and then plus another one where we have arbitrary constant times t. So then using our initial conditions, we can find that C1 is 0.16 and C2 is 0.48. You should verify that on your own. And that will give you that the critical damping solution looks something like this. Okay, so finally, the most interesting case, of course, is the underdamping. And here we're assuming that C is equal to 10. So this will give you this characteristic equation. And for time's sake, I've just sort of given you the characteristic values instead of going through the whole derivation. So we get negative 0.5 plus or minus 2.96 times I. So of course, that gives us the general solution where we have e to the real part times t, and then the sum of the sines and cosines with the imaginary part times t on the inside of them. Okay, so similarly as before, we can find our arbitrary constants a and b by using the initial conditions. And we get that our underdamped solution is given by this particular solution here. Now, to see a graph of all 3 of these, I think is nice and interesting and ties all 3 of these together. So if I can try and sort of point these out, I think it's obvious that this one on the outside is the underdamped one. Right, because that's the one where you have the oscillations sort of going on forever. Now, this one that goes to 0 very quickly is, of course, the overdamped solution, because that's taking the energy out of the system very quickly. And then this other one on the outside here is your critical damping. And that's giving you the solution sort of right before you start to experience these oscillations. All right, so that wraps up this video on looking at the mass spring system with unforced sort of oscillations. So I hope you enjoyed the video, and I will see you next time.